And welcome back, everybody. So in today's lecture, we are talking about moments and how we can use the moments of a distribution to find the mass of a contamination and other characteristics of transport, so the velocity and the dispersion coefficient. Okay, so as I've mentioned before several times, we know that the fundamental solution of the advection dispersion equation is a Gaussian, a bell curve. Now the good news is we know a lot. Now the good news is we know a lot about Gaussians, right? So from statistics, we know that 95% of the data is contained within 4 standard deviation. And we've seen before how we can calculate standard deviations from data. So there's a lot of things that we do know, right? So there's a rule of thumb, or I guess a practical, way to find the size of a plume, which is basically 4 sigma. So this is essentially saying, well, we don't really care about that last 5% of the mass or of the data, which, may or may not be true. Sometimes we actually do care about those last 5%. But in most cases, right, we want to clean up, so we want to remove most of the mass. And we're saying, well, when there's only 5% left, we don't really care. So the size of the plume is about 4 sigma. That gives us a good intuitive sense of how big, how far is that plume reaching, essentially. Okay, so I already discussed the problem with the peak, right? So we know that the peak gives us the mass and the dispersion. So peak is in 1D, right? Again, in 1D. We'll talk about dimensions later. But for now, in 1D, C peak equals m over square root of 4 pi dt, okay? And I also mentioned before that if we have pulses, right, or if we have data at 2 different times, so here, for example, this is, space, x, and this is concentration as a function of x, but we have 2 different times, so we can see that d sigma squared dt equals 2d, right? So we can calculate the dispersion coefficient if we have that kind of data. Okay, so this was just a reminder of everything we've done so far. Now, the characteristics, so as I mentioned before, right, basically there's only 3 things that define completely our system in 1D. Those are the mass, the velocity, and the dispersion, right? So there's only 3 parameters: the mass, the velocity, which is in here, sorry, x0 equals ut, if u is the velocity, right? So the velocity and the dispersion, that's it. There's only 3 parameters in this equation, and that's all we need to describe everything, right? Now we can, Now these 3 parameters can be calculated using the moments of a distribution, and the first 3 moments, I should say, 0, 1, and 2, describe completely the distribution. So we can, if we know how to use the moments, and if we have data, we can actually back calculate mass, velocity, dispersion somewhat easily. And that's true in space, and that's also true in time. Okay, so what are the moments, right? So the moment of a distribution are defined here, and the general definition is given here. So a moment, the ith moment, right, is the sum of the data to the ith power times f of x dx, okay? So for a concentration distribution, right, if f of x is c of x, let's call it, c of x, right, is our distribution. The 0th moment, so x to the 0 is 1, so that doesn't count. So cx dx, and that gives you the mass. Again, as a function of x, right? This is really important because if it's in time, that's not true anymore. And we'll see what it is in an exercise that you'll have to do for homework. Now the first moment, again, x to the I is x, c of x dx, right? And then the second moment, x to the I, so second, x squared times cx times dx. Now so that means if we know if we have data, right, cx is f of x, so if we know c of x at different x's in space, then we can calculate those moments by doing those operations here. They are very simple in Excel. You can just sum things over, right? Again, remember the integral is just a sum, so we can sum things over, find the moments, and then in turn find the mass the velocity in the aquifer and the dispersion coefficient for that aquifer and how fast this thing is moving and where it's going, essentially. So again, the mean is, so once you have the raw moments, so let me clean up a bit here. Once you calculate those raw moments, so from 0 to 2 here, these are the first 3 moments, right? Then you want to normalize them by the 0th moment, and this is really important. So the mean of the distribution, right? The mean of the distribution is the first moment divided by the 0th moment. So you need to renormalize those moments by the 0th moment. And then the variance of the distribution is actually given by the second moment normalized by the 0th moment minus the first over the 0th, okay, squared. So it's really important that you do this last operation to find your mean and variance, which again are what you want to define your velocity and your dispersion. Okay, so I have an example with a few questions, right, to kind of explain how we use the moments to find, a real life scenario. And I'll cut this video here, this intro video here, and then I'll continue in the second video just so it doesn't run too long. All right, thank you. I'll see you in the next one.